our last lesson, 6.7, integration by substitution. This is so exciting because when you get done with this lesson and after you've practiced this integration by substitution, you will be able to integrate a lot of things. You still won't be able to integrate everything. There's some more integration that you'll learn in Calc 2, but this will get you to the point where you can integrate a lot, okay? And just to think about it, you know, if you have something like the integration of secant x tangent x, you're thinking, I know that that is the derivative of secant x, right? So you're always thinking of this as the derivative, right? You're thinking, if that's the derivative, what could my original function have been? And then you'd say, oh, that could be secant x plus some constant, right? Because I know that the derivative of secant x is secant x tangent x. And the same thing goes for like cosecant squared x. Even though this derivative would have been negative, right? But if I think of the original function as negative, then that makes me have my derivative of that negative function to be positive cosecant squared. And so, excuse me. And so, you know, that's what I want you to be thinking of. I want you to be thinking of, do I know that this is just the plain derivative of something, you know, or the negative of the derivative of something? And so when you have a situation like that, taking the integral isn't too difficult. But when you have to use substitution is when there's something there that isn't that easy. So let's start reading about it. So the key to use substitution is finding a piece of the function whose derivative is also in the function. The derivative is allowed to be off by a coefficient, but otherwise must appear in the function itself. And the role of substitution in integration is comparable to the role of the chain rule in differentiation. So our procedure for using U substitution, we are going to look for a piece of the function whose derivative is also in the function. If you're not sure what to use, try the denominator or something being raised to a power in the function. We're going to set U equal to that piece of the function and take the derivative with respect to the variable. And then we're going to use your u and du expressions to replace parts of the original integral, and your new integral will be much easier to solve. So what I also want to show you is when we're integrating something like sine x dx, okay, I know that, okay, the derivative of cosine is negative sine. So this would be negative cosine x plus c, right? And that's fine, okay? This is just, you know, that was your the negative of your derivative. But what if you had something like the sine of 2x dx? And you're like, well, how would I get that as a derivative? I know it's something to do with cosine 2x. I'm just not sure. So what we can do using u substitution is we can say, what if that was just a u? Okay, so over here I'm going to say, what if that was, that u was 2x? Then if I took du, which is just the derivative of u, and then I'm going to take the derivative of x is just going to be 2 dx, and then solve for dx. So I would divide by 2 on both sides. Then I would come back over here and I would say this is sine u, and then I would substitute for dx. And so now you can see this is 1/2 du. So I'm going to bring this 1/2 in front times the integral of sine u du. And so this is 1/2, and then this would be negative cosine u plus c, and then I put my u back in. So once I put my u back in, now what I'm going to do is I'm going to check this by taking the derivative of it. So I'm going to take d dx of negative 1/2 cosine 2x plus c. And I'm going to see, do I get this derivative? Because if I do, then my answer is correct. Okay? I'm trying to see if this answer right here is correct. So let's try it. So I've got my negative 1/2. The derivative of cosine 2x is negative sine 2x times the derivative of 2x. And the derivative of my c is 0. So now I take this 2 and cancel it with that one. This one's in the numerator. This one right here is in the numerator. This one's in the denominator. They cancel. Negative times a negative is a positive. And look, I do get what I started with. So I do have the correct answer to my integral. Okay, so that was using U substitution. And what you want to be thinking of here is you're thinking that this, is like the chain rule. You're thinking of it as it's not just sine x, it's sine 2x. So it was created by f of x equals the sine of x and g of x equals 2x. And it was you putting 2x into the x. So this was f composition g of x, the sine of 2x, where I put my g of x function into the x in my f of x function. So this was, composition function. Sorry, couldn't think of the word composition. All right, so now let's go back over here and let's think. Because if you can see, we looked for a piece of the function. Well, we didn't really do part 1 because the derivative of 2x was 2. So I didn't need it. If it's a constant, you just, that's why they're saying here, the derivative is allowed. Up here it says the derivative is allowed to be off by a coefficient, which, so it was off by a 2. There was a 2 that was missing, but that's okay. Because that derivative of 2x was 2. So that is okay. But we set u equal to the piece of the function, that we wanted to, that we knew we were going to have to take the derivative of. And then we used our u and our du to replace and solve the new integral, because that made it an easier integral. So now, the substitution method for indefinite integrals. Substitution is a method of integration designed to undo the chain rule. It generally involves 3 steps. So again, we are going to undo the chain rule, right, when we're using our substitution method. So look at what they've given us here. Do you see how our integral, I've been telling you now that this is your derivative. Well, that makes sense if we had a composition function. Remember what the derivative of our composition function is. It's f of g of x, or f prime of g of x times g prime of x. But, that's looking at this f as your derivative. Okay? So, step 1, we're going to integrate f of u du. So we're going to let u equal g of x, and then du equals g prime of x. Step 2, capital F of u plus c. So we're finding the antiderivative of that little f of u and make it capital F of u. Step 3, capital F of g of x plus c. Substitute the g of x back for u. Just like we did here, we substituted. Once we found the derivative right here with respect to u, then we substituted our 2x back in. We substituted our u back in. Okay, that's what they're talking about. So now, we've got our outside function, which is our little f, which is actually our derivative. We've got our inside function, Okay, so that's like your 2x for the one we just did. Then you've got the derivative of this inside function. Well, that was what we were missing, but a lot of times you're looking for that. And we'll do an example so you know. And then you've got your antiderivative of g of x plus c. So the general power rule for integration, if g is a differentiable function of x, then the integral of g of x to the n times g prime of x dx is g of x to the n plus 1 divided by n plus 1 plus c, provided that n does not equal negative 1. So equivalently, if u equals g of x, then the integral of u to the n du is u to the n plus 1 over n plus 1 plus c, where n is not negative 1. If n were negative 1, you would have natural log as your integral. All right, so now let's look at this first one, A. So a lot of times I'm going to tell you that you are looking for something to a power, right? That is going to be your u, okay? Or square root of something. That will be your u, what's underneath the square root. So this guy right here, if I made that my u, when I take the derivative, so du would be 2x dx, do you see my derivative here? I do. I see that 2x. So then you're going to solve for dx, and this will be the integral of u squared. Go ahead and leave your 2x in there, and the reason why is because it's going to cancel, okay? Sometimes only the x cancels, and you have to pull the 2 out in front, but this time the 2 and the x are going to cancel. And now you're just left with the integration of u squared du. Well, that's easy. That's u to the third over 3 plus c. And then you put your u back in. So our u was x squared plus 1, to the third over 3 plus c. And that is our final answer. And if you want to check it, you can take the derivative of this to check it. And I don't know if that's something that you guys want me to do or if you want to do on your own. But we can. Maybe we should do it on the first one. If we took the derivative of, this is like 1/3 x squared plus 1 to the third plus c. So if we took that derivative, the 3 would come down times the 1/3. Okay, giving you 1 x squared plus 1 to the second times the derivative of x squared plus 1, and then the derivative of c is 0. So this would give us x squared plus 1 squared times 2x. And when we look back here, we had x squared plus 1 squared times 2x. So we did get the correct, we did get the correct answer. So check, that one is good. Yay, that's great. All right, now let's do B. So this one, here's like, these are ways to look for what to make u. Okay, because you're trying to decide, what do I make my u? You know, because some kids are going to go, oh, well, my u is cosine 4x. Well, no, you can't make your u cosine 4x. That's a bad idea. You don't want to do that. Okay, you don't want to do that. You only want to make it because then you won't have anything to integrate, right? So, and plus, look what happens when I make my u cosine 4x. My du becomes negative 4 sine of 4x dx, and then nothing cancels. Like if I then say, okay, my du divided by negative 4 sine of 4x equals dx, and then I come here and I go 4u, because that's what I made my u, and then I put in my du over negative 4 sine of 4x, well, I'm just in a pickle here because I don't have anything that cancels that sign. So see, that would not have made sense. So you don't want to do that. you didn't have a sign, like the derivative of your u has to be there, or it can be like a constant away. So I hope that you're thinking like cosine u or sine u. So your u would be 4x. Then your du is 4 dx. And your du divided by 4 is your dx. So now you can say integral of 4 cosine u times du over 4. And see, now your 4's cancel. And you're left with the integral cosine u du. And now, what can you take the derivative of that will give you cosine? That should be sine. So you're saying, okay, if I took the derivative of sine, I would get cosine. So therefore, sine u plus c. And so this would be sine, now I'm going to put my u back in, 4x plus c. And you can check your answer. If you take the derivative of sine 4x, it's going to be cosine 4x times 4, which is 4 cosine 4x. And so that does give you back your function that you know was the derivative, okay? It gives you back that function. All right, here's our next one. Do you see something that if you took the derivative of it, then you see that derivative somewhere, okay? And I hope that you're thinking, oh, well, if I took the derivative of this, it would be 8x, and oh, look, it's right there. You see how 8x is right there? Oops, that one doesn't draw. I tried to draw an arrow. It doesn't draw an arrow very well. So you could also, since it's easy to make it everything underneath the root, what if I made that my u? Is my derivative still there? Since the derivative of 1 is 0, yes, my derivative is still there. So let's go ahead and make that whole thing underneath the root your u. Because when I take my du, and that's going to be 8x dx, and my du divided by 8x is my dx, and you see how I'm going to substitute that in for dx here. I'm substituting this with a u, and then my 8x is going to cancel. So I'm going to keep my 8x here. This is going to be the square root of u, and then this is going to be du divided by 8x. Okay, I just kept my 8x, I put in my u, I put in my equivalency for dx that I found here by taking the derivative of u. Now I can see that my 8x's are going to cancel, and so I've got integral, and I'm going to make this u to the 1/2 du, and then that's going to be u to the 1/2 plus 2/2 divided by 1/2 plus 2/2 plus c. So this is u to the 3/2 and then divided by 3/2 plus c. So this is going to be 2/3 u to the 3/2 plus c. Now I got to put my u back in. So I did a lot of simplifying. I wanted to show all my work just in case anyone was having trouble. And now I'm putting my u back in. And that is my answer. Had to go around that. Okay. So if you wanted to try and take the derivative of that, then you can okay, I just realized why the black and the red are so fat, because I've got them selected to be a lot fatter than the others. Okay. So if you took the derivative of that, you should get your entire function here. That should be, that whole derivative there should be what you get when you take the derivative of your answer. Okay? So I'll go ahead and just erase that. So get that problem back on there. Okay, so now let's try this one. So again, I should be thinking of, you know, u to a power, square root of u, cosine u, sine u. It might be ln u, you know. So if you see this and then you want to find out if I made that whole thing, because that's to my power 3, my third power, if I made that whole thing my u, and I took the derivative of it, is it going to get rid of this other x here? Because if it doesn't, then I got to do something else, okay? So I'm going to solve for dx, and I've got integral x times u to the third times du over 2x. And do you see now how this x and this x cancel? I still have a 2 there, but that's okay. Let's pull it out. It's in the denominator. Pull it out as 1/2. And now you only have u's left. Remember, if I did not put my u in here, if I left this dx here or anywhere here, you know, anywhere where we were putting du, then we would have to integrate with respect to x, which doesn't make sense, right? You have to integrate with respect to the variable that you're using. So when I change this main thing to u, I've got to integrate with respect to u. So if I have any x's there, it gets me in trouble. I can't do it. I've got those x's there. These have to all be in terms of u. There can be constants. It's fine. You can pull them out in front, and then you don't have to worry about them. But you can't have two different variables there. So we're going to bring the 1/2 down. This is going to be u to the 3 plus 1. So that's u to the 4th divided by 4. And then plus c. And so this is going to be 1/8, because 2 times 4 here in the denominator. And then I'm going to put my u back in, x squared plus 2 to the 4th plus c. And again, if I take the derivative of that, I should get back to my original function right here, this derivative. Okay, this should be the derivative of this answer. And you can check it just to make sure. Okay, here we go again. I see something to the 6th power. If I take the derivative of this, I get 8x. I think it's going to cancel that x out. I hope. So hopefully you saw that we should make our u 4x squared plus 3. Our du is 8x dx. Our du divided by 8x is dx. I accidentally hit that button. So now over here, integral of, remember you're going to leave that x because you only made this your u. X over u to the 6th, and then you're going to substitute dx with du over 8x. And then you can see that these x's do cancel. So that's perfect. And you can pull the 1/8 out front integral and make this u to the -6 du. Because that's going to be the easiest thing to do, is bring that u to the 6th up. So 1/8, and then this is going to be times u to the -6 plus 1. So that's going to be -5 divided by -6 plus 1. So divided by -5 plus c. So I've got a -1/5 times a positive 1/8 is a -1/40. And then put my u back in, 4x squared plus 3 to the -5th plus c. Or, and you could leave it like that, -1 over 40 times 4x squared plus 3 to the 5th in the denominator. So, plus c. So you could have left it like this. That would have been fine. Or you could have made it like this. Either one of these, if you took the derivative, you should get back this function right here, right? That should be the derivative of your answer. Okay. Now you can see I said square root here, or any root. Cube root also, you probably want to make what's underneath your cube root u. And I mean, there's different situations where it might not work. But look, if I made 7 minus 2x cubed my u, and I took the derivative, it would be negative 6x squared, and then I'd get rid of that x squared. So let's make our u 7 minus 2x cubed. Our du is negative 6x squared dx. So du divided by negative 6x squared is my dx. This becomes the integral of the cube root of u, now times x squared, and then put your dx equivalency in. And then you can say, okay, look, my x squared in the numerator goes away with my x squared in the denominator. And so I'm going to pull my negative 1/6 out times the integral of u to the 1/3 du. Okay, because that negative 6 was in the denominator, so it came out as a negative 1/6. Now I've got negative 1/6 times u to the 1/3 plus 3/3, because I have to add 1. So I'm going to make, if my exponent has a denominator of 3, I'm going to make my 1 3/3, and then divided by my 1/3 plus 3/3 plus c. So negative 1/6 u to the 4/3 divided by 4/3 plus c is going to be negative 1/6 times 3/4 u to the 4/3 plus c. And then I can say divide by 3 I get 1, divide by 3 I get 2. So this becomes negative 1/8. And put your u back in. 7 minus 2x cubed to the 4/3 plus c. Okay, I just glanced at my answer here, and I realized that I did not see this 4, guys. So let's go ahead, and instead of stopping this thing, and our u is okay, so you probably don't have to erase your u, but I just accidentally did. So our u was fine and our du was fine, but I just left out that 4, so it should have been u to the 4/3 instead of u to the 1/3. I just overlooked that little 4 there. So let's try and do this one over. I'll do it over in a different color so that we know which one is the new one, because my eraser is not going very fast. So you guys, if you left your u equals 7 minus 2x cubed, and your du was negative 6x squared dx, and du divided by negative 6x squared is your dx, then over here, do you see what I was talking about? I did not see that u to the 4th, and so it's all it would have done is made that to the 4/3 instead of to the 1/3. Everything else is going to be the same. So you guys could go back and quickly fix yours, just changing that 1/3 to 4/3. But for me, I had to do it all over again. Sorry about that. So there's what we would have gotten there. This eraser is slow, slow, slow. Slow Joe. All right. So now And I also, it just doesn't want to erase. I also went and kept the blue. So now, negative 1/6, geez, I'm a mess. Negative 1/6 u to the 4/3 plus 3/3 divided by 4/3 plus 3/3 plus c. Negative 1/6 u to the 7/3 divided by 7/3 plus c. Negative 1/6 times 3/7 u to the 7/3 plus c. So now I can say divide by 3, I get 1, divide by 3, I get 2. Only this is going to give me negative 1/14. And then this is times 7 minus 2x cubed. I'm putting my u back in, to the 7/3 power plus c. Now that is what I got on my paper. Sorry about that. I always check it just real quick. And I just checked it, and I was like, oops, did something goofy. All right. So now let's go to the next page and look at our example number 2. Those were all really good. And you might want to try and tackle some of these on your own, but you might want to just wait till the homework, because these get harder because they're trig functions. And the trig functions are just a little bit trickier sometimes. So here we go. So what do we know that tangent is equivalent to? Because I don't know anything that if I take the derivative of it, I just get tangent. Like if I looked at all my trig derivatives, none of them give me tangent as a derivative. So I'm going to have to do something different. So what I'm going to do is make this sine x over cosine x. And then the little trick is to always, like if you have to do something like this, make your u the denominator, okay? It always seems to work, and I'll show you why. If I take my du, I'm going to get negative sine x dx. And then when I divide, it's going to easily cancel with my numerator, okay? So that's why most of the time that it works. Oops. And so this is going to be integral sine x over u. See, I'm putting my u in. I'm putting my equivalency for dx in. And look, my sine x's cancel. So I've got negative integral. I just brought the negative out front. So negative integral of 1 over u du. Now remember, we would not make this u to the negative 1 because that's the only thing where our x to the n doesn't work. So when when you're doing that and you're trying to solve an integral, n can't be negative 1. Because if it were negative 1, then your answer is going to be natural log. So we're going to say, okay, this is negative, and then natural log of the absolute value of u plus c. And so then I put my u back in, negative natural log of the absolute value of cosine x plus c. And that's the integral of tangent. And you always have to do absolute value because you cannot have 0 or a negative as your argument. Okay, so cosine x cannot be 0 and it cannot be negative. So let's look at b. B is going to be handled the same way. We put our equivalency for cotangent in. It's going to be cosine x over sine x dx. So that's just a trig identity that we know cotangent is equivalent to that, okay? And then, like I said, make your u what's in the denominator. So this time we're going to make our u sine x. Our du is going to be cosine x dx. And then our du divided by cosine x is dx. So now we come over here and we say, okay, I'm going to leave my numerator alone. My denominator is going to be u, and then this is going to be du over cosine x. And my cosine x's cancel. So this is the integral of 1 over u du. And so that one is just ln of the absolute value of u plus c. And now you have to put your u back in. So the integral of cotangent x is ln absolute value sine x plus c. Okay, so those aren't too bad. You just have to, use that trig identity. Because there was nothing that we have that is a derivative that equals tangent, nothing that is a derivative that equals cotangent. Do we have anything that's a derivative that equals secant? So this one's even weirder because we don't. So this time you're going to multiply this by secant x tangent x over secant x tangent x. I'm sorry, secant x plus tangent x over secant x plus tangent x dx. This is a fraction that equals 1. So, if you have the same thing in the numerator and the same thing in the denominator, then you can multiply. What does this give us? Secant squared x plus secant x tangent x, all divided by secant x plus tangent x dx. So now think about this, okay? The derivative of tangent, which is the second thing here, equals secant squared, okay? And the derivative of secant is secant x tangent x. So my entire numerator is the derivative of my denominator. So I'm going to make my denominator my u. So we're going to let u equal the denominator, secant x plus tangent x. And then when we take the derivative of it, the derivative of secant x is secant x tangent x, plus the derivative of tangent is secant squared x. And then that would all be dx. And then, of course, you would divide by that. And I'll go ahead and make it so that my secant squared x is first, and my secant x tangent x is second, just so it looks like my my numerator there, so that when I put all my stuff in, it makes sense. So I've got my integral of, and then I was going to leave alone my numerator. My denominator is u, and then I'm going to replace dx with du over secant squared x plus secant x tangent x. And you should see that this whole thing and this whole thing are exactly the same and they cancel. Okay? So then that's going to leave us with the integral of 1 over u du, which is going to be ln absolute value of u plus c, which is going to be ln absolute value, and our u was our secant x plus tangent x, and then plus c. Now, do I think that you would have somehow known to multiply this by secant x plus tangent x over secant x plus tangent x? No. I don't know how to tell you, oh, well, this is the one way you just have to kind of think about things. I don't expect that you would have gotten that one, but I wanted to just show you that you can use trig equivalencies, and you can use fractions that equal 1 to get things so that they're in a format where you can actually integrate them. Okay, there are ways to make it happen. I didn't say that it was always going to be easy, though. This next one is another example of how it's not going to be easy to do something like this all the time. So I've got the cosecant of x. I know that there's nothing that that you take the derivative of that will give you just plain old cosecant. I know negative cosecant squared, but I don't know anything that's just cosecant. So I'm going to multiply by cosecant x plus cotangent x over cosecant x plus cotangent x. So this is my fraction that equals 1, and as long as I multiply by a fraction that equals 1, I still have the same integral. So I'm still integrating just cosecant x, only I'm going to make it look different. So now I distribute that outside cosecant to my numerator. Remember, this is like over 1, so your denominator is going to stay the same, but this is going to become cosecant squared x plus cosecant x cotangent x divided by cosecant x plus cotangent x dx. And so think about what your derivatives are. The derivative of cotangent is negative cosecant squared. The derivative of cosecant is negative cosecant x cotangent x. So it's almost the same, where my derivative of cotangent was, here, and my derivative of cosecant is here, only just difference by a negative. So I'm going to let u be my denominator here. And then when I take the derivative, like I said, we have the derivative of cosecant is negative cosecant x cotangent x plus the derivative of cotangent is negative cosecant squared x. And that be dx. That whole thing dx. And then your du divided by, I'm going to factor the negative out, and that will be negative cosecant x cotangent x plus cosecant squared x. And then that equals my dx. So now over here I've got cosecant squared x plus cosecant x times cotangent x divided by, I'm going to put my u in, and then multiplied by du over negative times the quantity. And let's go ahead and put it in the same format. I can put this first and that second if I want to. It doesn't change the value of it. I am running into my other problem, though. Sorry about that. So let's just put a little wiggly sign down there so that we don't get those mixed up. And you can see here that this is exactly the same as this. Now there's still a negative there, so we can't forget that. We'll pull that negative out in front, and this will be 1 over u du. So this is negative ln of the absolute value of u plus c. I'm going to pull it all the way over here. Negative ln absolute value, and my u was cosecant x plus cotangent x plus c. And there is my integral of cosecant x dx. Again, I don't think that you would have thought of that on your own. So please don't think that I'm going to give this to you and you're going to have to think of it. But I want to show you, this is you starting to have some experience with trig identities and what we can do with them. Okay, example number 3. Rewrite or expand before integrating. So what they want us to do is get your trig identity sheet out. So stop the video, get your sheet. I think some of you have it's bright blue, some of you have other colors, and I want you to look up what sine squared x is equivalent to. And the reason why we're not going to be able to just go, oh, well, let's just make this the sine of x squared and then make that my u. But my derivative is cosine, and there's no cosine there to cancel. So I cannot do this. If you don't use a trig identity, you cannot solve this integral. You have to use a trig identity to make it something that you can solve. So if you saw on your sheet 1 minus the cosine of 2x all divided by 2, that is the one you want to choose, and we want to break this up as 1/2 minus 1/2 cosine of 2x, okay? Because you can do that. Put the 2 under the 1, put the 2 under the negative cosine 2x, and that's the same thing as 1/2 minus 1/2 cosine 2x. So now, I know that sine squared x is equivalent to this. They are exact equivalents of one another. Therefore, the integral of sine squared x dx is equivalent to the integral of 1/2 minus 1/2 cosine 2x dx. Okay, so I'm just putting that in as an equivalency. And I want to break this up into two separate integrals. Okay, so I can do that. 2x. And then this would just be 1/2 x, right? That integral's easy. This one, I'm going to bring the 1/2 out, and we're going to use u substitution because we want our u to be 2x. Our du is going to be 2 dx. So our du divided by 2 is our dx. So we already integrated the first one. It's just 1/2 x, right? If that's a constant, then it's getting multiplied by x. That's easy. Oops. The second term, we're going to make it integral cosine u times du over 2. And we're going to pull that 1/2 out. It's going to give you negative 1/4. So I'm just going to go down here. So my first term, 1/2 x, and then this is going to be minus 1/4 because 2 times 2 in the denominator, I'm pulling that one in front. Oops, times the integral of cosine u du. And so 1/2 x minus 1/4, and now integral of cosine u is sine u, and then we have our plus c, and now we need to put our u back in. So 1/2 x minus 1/4 sine, put that 2x back in, plus c. So that wasn't too bad. We just had to use that trig identity. And then the next one, so we rewrote the first one. This one we're going to expand. Okay, we're going to take this binomial times itself. We're squaring it. And what would we get? Well, this is going to be the integral of sine squared x plus, and then we've got a sine x cosine x and another sine x times cosine x. So plus 2 sine x cosine x, and then plus cosine squared x, and that whole thing dx. Because I just multiplied it out, that's what I should have gotten. Now, does anybody remember the rock star? The rock star is sine squared x plus cosine squared x equals 1. Do you see how if I move this cosine squared x up in front with next to the sine squared x, I can take this and I can go, well, I know that's 1. Well, that's what you want to do for this one. Okay, sine squared x plus cosine squared x is 1. That should be on your trig identity sheet also. Okay, that's the easiest one to remember. Now you can break this up. The integral of 1 dx plus, and I'm going to bring the 2 out in front, integral sine x cosine x dx. So you break that up into two separate integrals. And your integral of 1 dx is just x. And this next one, I'm going to make my u, I don't think it really matters exactly what you make your u. You could make it sine or cosine, but I'm going to make it sine. And then my du is going to be cosine x dx. So my du over cosine x is going to replace my dx. Okay? So this is going to be integral, there's my u for sine x, here's my cosine x, and then I put in my equivalency for dx is du over cosine x, and you should see that those cosine x's cancel, leaving me with just my, just my du there, okay? So now let's pull this down. We've got x plus 2 times the integral of u du. So x plus 2 times u to the 1 plus 1 divided by 1 plus 1 plus c. 2's cancel. Put your u back in. So x plus, this is going to be sine of x quantity to the second power plus c, which also can be written as sine squared x, right? X plus sine squared x plus c. And, and that is your answer, okay? If you took the derivative of that, you should get what you started with here, okay? You'll get this as your derivative if you take the derivative of this guy right here, okay? You can always check your work by doing that. Okay. So now, this is a long lesson. I'm so sorry. You might want to take a break here. I'm going to go ahead and keep going. If you want to take a break, this is a good time because we're going to do definite integrals now. And when you use u substitution, there's something special that you have to do when you're using u substitution with definite integrals. That means you're going to have, values, and your answer is not going to be a function. It's going to be a number. So, if you want to come back to this, that's fine. All right, so I'm going to keep going. Changing the limits of integration when solving definite integrals. So when using u substitution with a definite integral, it is convenient to determine the limits of integration for the variable u rather than to convert the antiderivative back to the variable x and evaluate at the original limits. So when you're looking at an integral like this, on a, these values are x values. This is like x equals 0 to x equals pi over 4. And you are, integrating with respect to x. So when we change it and we're integrating with respect to u, we have to change these so that these are u values, okay? And then you don't have to put your x back in when you have a definite integral. You can, if you change these to u values, and this whole thing's in terms of u, you don't have to put your x back in. You can just keep going and get your answer with your u values and your function in terms of u. But, if you started out with x's, don't put these same numbers in for u's. That won't work. It will not give you the right answer. So, substitution in definite integrals. When we integrate over an interval a,b, the values of a and b are x values. The use of u substitution requires a change in ab to g of a, comma g of b. So the integral from a to b is of f of g of x times g prime of x dx equals the integral of g of a, or from g of a to g of b, f of u du. Okay? So those have to be u values, and they start out, if you're differentiating with respect to x, they start out as x values. Okay? Or if you were differentiating with respect to t, they would start out as t values. You know what I mean. Whatever this integral right here is with respect to, then that's what you're differentiating. That's what these values a and b are. Okay, so now, do you see something that you could make your u that you also know the derivative of it is there also? So my choices here are, do I make my u tangent x? Do I make my u secant squared x? Do I make my u secant x? Okay? And I think the easiest thing to do is to make your u tangent x. okay? Because your du is secant squared x dx. And then when you solve for your dx, you're going to see, and what I like to do on these definite integrals, I just don't put anything the first time, right? I'm exchanging tangent x with u. I'm leaving my secant squared x alone, and I'm putting in du over secant squared x for my dx. And then my secant squared x's cancel. So now I want to go back and I want to say, well, okay, I need my u's here, okay? I need these to be u's because I'm getting ready to do the integral of u to u. So if my u is tangent x, then for u equals 0, I'm sorry, for x equals 0, what is my u? Well, the tangent of 0 is 0. So my u is also 0 down there. And for x equal pi over 4, if I put tangent of pi over 4, my u is 1. So this one goes from 0 to 1. And now I don't ever have to put my tangent back in. Okay, I don't have to because these are all u's now. I can just say u to the second over 2. Oops, I almost said plus c, from 0 to 1 is going to be 1 squared over 2 minus 0 squared over 2. So my final answer is going to be 1/2. And remember how I said a definite integral has an answer that is a number. When you're integrating a definite integral, it's going to be a number. When you're integrating an indefinite integral, it's going to be a family of functions. And the reason I say a family of functions is because you have your plus c. Okay, so for b, notice that this bottom one is to the third power. So I'm thinking that I want to take and make my u whatever would be taken to the third power. So I'm going to make my u cosine of 2 theta. So that when I go here, I'm going to make this sine 2 theta over u cubed, and then I'm going to put my d theta in. So when I take the derivative of this, the derivative of cosine 2 theta is negative sine 2 theta times the derivative of 2 theta. And this would be d theta, not dx. So this is going to be negative 2 sine 2 theta. Remember, we always bring that constant in front, like I did here, d theta. And so this will be du over negative 2 sine 2 theta, and that will be my d theta. So here I will put du over negative 2, and I'm going to erase that so I can have some more space, sine 2 theta. And look, my sine 2 thetas cancel, and that leaves me with just u's. So I've got negative 1/2 that I pull out in front. This is going to be u to the negative 3 du. Now, remember, these are theta values. These are thetas. My u, I need to figure out what my u is when my theta is 0. So this would be 2 times 0 would be 0. So this u is the cosine of 0. So that's 1. So this bottom one is going to be 1. And then what is my u when my theta is pi over 6? So that would be 2 pi over 6, which would be pi over 3. And so if you think about what you have at pi over 3 is 60 degrees. So that's going to be square root of 3, 1, and 2. And my cosine is 1/2. So my u is 1/2. Now, here's the problem. This is not the smaller one. The smaller one happens to be on top, so we got to flip them. Well, when we do that, it negates it. So this becomes positive 1/2 integral from 1/2 to 1 u to the negative 3 du. So positive 1/2, this is going to be u to the negative 3 plus 1, so u to the negative 2 divided by negative 2 from 1/2 to 1. Notice I'm not going to be putting my x back or my theta back. I'm not going to be substituting cosine 2 theta back in because I changed everything to u's. So this is going to be negative 1/4 times, I'm going to make this 1 over u squared from 1/2 to 1. So negative 1 over 4u squared from 1/2 to 1. So negative 1 over 4 times 1 squared minus negative 1 over 4 times 1/2 squared. So negative 1/4 plus 1 over, and this would be 4 times a fourth, right? Because 1/2 times 1/2 is 1/4, and 4 times 1/4 is 1. So I actually have 1 minus a fourth, which we know is 3/4. So that integral becomes 3/4. That's your answer to B. And I know that these are challenging, guys. So just bear with me, and we can get through this. All right. So now, hopefully you see something here that if you took the derivative of it, you're going to get this out here. And we can make it just the whole thing underneath the root. And I hope that you saw that when you took du, you get 3x squared dx. And that's what I see on the outside of my root. So that really works out nice. So don't put your 0 to 2 there, because remember, those are x's. Those are x's, and we're getting ready to make this all in terms of u. So this is square root of u times du over 3x squared. So my 3x squareds cancel, and I end up with integral u to the 1/2 du. And then we need to figure out, since our u was 1 plus x cubed, what is my u when my x is 0? And so when my x is 0, my u is 1. So I'm going to put 1 down here. And then I want to find out, what is my u when my x is 2? That'd be 1 plus 2 cubed, which is 1 plus 8, which is 9. So we are actually integrating from 1 to 9, u to the 1/2 du. So this is going to be u to the 1/2 plus 2/2. And then that's u to the 3/2. And then division by 3/2 is multiplication by 2/3 from 1 to 9. So this is going to be 2/3. And then, of course, my denominator is 2. So that's a square root. So I've got square root of 9 to the 3rd power minus 2/3 square root of 1 to the 3rd power. So that's going to be 2/3 times 3 to the 3rd minus 2/3 times 1 to the 3rd. So this, one of my 3's goes away with one of these. So this is 2 times 9, which is 18, minus 2/3. So 54/3 minus 2/3 is 52/3. And that would be my answer to that integral. Okay, notice I did not put my u back in with a definite integral. We changed our limits of integration to u values, and we left our u in there, okay? That's the main thing that you need to learn from example 4, okay? And, you know, just what to do with those definite integrals, changing those limits of integration to u values from x values or from theta values. All right, one more. One more. See if you can imagine what you're going to make your u. So hopefully, you could just make it like 5x squared, or you could make it 1 plus 5x squared. But when you take the derivative of 5x squared, you get 10x, and that's going to help you cancel those x's, that other random x that's up there. So let's say we make our u the whole denominator, 1 plus 5x squared. Our du is going to be 10x dx. So du divided by 10x is my dx. And so this is going to be the integral of x over u times du over 10x. And my x's cancel. Thank goodness my x's cancel. So I end up with the integral of integral of 1 over u du. Okay, so pull that 1/10 out, then you don't have to worry about it. We do need to find our limits of integration. Our u is 1 plus 5x squared. So what is our u when our x is 0? So our u would be 1 if our x is 0. So down here I put a 1, because here I'm going from x equals 0 at the bottom to u equals 1 at the bottom. And then I want to go from x equals 1. What is my u? So that would be 1 plus 5 times 1 squared. So 1 plus 5, my u is 6. So this is going to go from 1 to 6. So I've got 1/10 integral from 1 to 6, 1 over u du, 1/10 natural log of the absolute value of u from 1 to 6. 1/10, and then we've got ln of 6, and you can pull that 1/10 out in front and just do ln 6 minus ln 1 if you wanted to, or you could have made the 1/10 be on both of them. ln 1 is 0 though, right? So this is just going to be ln 6 over 10, or 1/10 ln 6, either way. And then our last 4 problems. We are going to practice another technique that you should have in your toolbox when you go to try and integrate something. You can use long division and completing the square when you're wanting to integrate. So when I see this division right here that I'm trying to integrate, what I would do is I would say, well, okay, I'm going to look at what this function, this divided by this, is equivalent to, because you know the quotient of it is going to be what happens when you get that integral. So what times x is x cubed? That would be x squared, and x squared times x cubed, x squared times 1, 1x squared, and then I subtract, which changes that to a minus and that to a minus. That goes away. This becomes positive 3, and a negative 1 is a positive 2x squared, and I'm going to bring down my negative x. And then I say, what times x is 2x squared? That would be 2x. I take 2x times x, 2x squared. Then I take 2x times 1, 2x. Then I subtract. Changes that to a negative, that to a negative. And so this goes away. This is negative 3x. I bring my negative 3 down. What times x is negative 3x? Negative 3. So negative 3 times x, negative 3x. Negative 3 times 1, negative 3. But then I subtract, which changes that to a positive, that to a positive. That goes away, that goes away. So this divided by this is actually exactly this. So what I'm saying is that I can now say, oh, well, this is the same thing as the integral of x squared plus 2x minus 3 dx, because that is what it equals, exactly, with a remainder of 0, right? We got 0 here. So if you got your remainder of 0, that means that this divided by this equals this. And now I can just easily say this is going to be x to the 2 plus 1 divided by 2 plus 1. And this one's going to be x squared, right, minus 3x plus c. So that one, we used long division, and then it made it very easy to integrate. Okay, let's try it on this next one. We've got x squared. You remember you have to put your 0x minus 4 here, and then you've got your x squared plus 1 on the outside, because it's top divided by bottom. So it's inside divided by outside. So what times x squared gives me x squared? That'd be 1. 1 times x squared is x squared. 1 times 1 is 1. And I skipped my 0x here because I didn't need it. You don't know if you're going to need it, so you might as well just put it in there just in case. If it's 0, then you can just make it go away. This goes away. I don't have anything here, so I've got 0x, and this is negative 5. So that tells me that this is equivalent to the integral of 1 minus 5 over x squared plus 1. Okay, dx. And so now I'm going to break that up into two integrals. The integral of 1 dx minus 5 times the integral of 1 over x squared plus 1 dx. This integral needs to, you need to pay attention to this. So star, 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 star. Do you remember that the derivative of inverse tangent was 1 over 1 plus x squared? Do you remember that? Because look, that's your derivative there. So this is going to be inverse tangent x. So this is going to be x minus 5 inverse tangent x plus c. So it looked like it was going to be hard, but actually it wasn't. You should have known that you couldn't use u substitution here because you didn't have an x. So I couldn't have made that my u because there was no x to cancel. So I knew that I couldn't use u substitution, okay? Because my derivative would have been 2x dx, and I didn't have another x there for it to cancel. But it all worked out because it was inverse tangent. Okay, what about completing the square? So for this one, you want to take your x squared minus 8x plus 16, and you didn't really have to complete the square on this one because it was actually factorable. So this is going to be a negative 4 and a negative 4, right? So, oops, this is x minus 4 squared. So this one was a little different, so I can say this is the integral of 5 divided by x minus 4 squared dx. And then I could use u substitution. I'm going to say, well, my u is x minus 4. My du is 1 dx. So if I made this 5 over u squared, and then I changed my dx to du, this could be, I could bring the 5 out in front. This could be u to the negative 2 du. And then I can say, oh, this is 5 times u to the negative 2 plus 1 divided by negative 2 plus 1, right? And so this becomes negative 5 over u plus c. And then you put your u back in. Negative 5 over x minus 4 plus c. So you didn't actually have to use completing the square unless you couldn't factor it. So if you couldn't factor it, then I guess you could have. But now this next one is not factorable, okay? So you are going to have to use completing the square on this one. So I'm going to leave a space, plus 2, leave a space, okay? And I'm going to take this guy right here, and I'm going to divide it by 2 and square it. 1 squared is 1. So I'm adding 1, I'm subtracting 1. And so my perfect square is x plus 1 squared, and then I've got plus 1, right? Because a positive 2 here and a negative 1 gives me a positive 1. So I did have to complete the square on that one. So this one becomes integral of 3 over x plus 1 squared plus 1 dx. So for this one, you're going to pull the 3 out and make that x plus 1 your u. So we're going to say u is x plus 1, du is just 1 dx. So I'm going to pull my 3 out. This is going to be the integral of 1 over u squared plus 1. And then I can just substitute du for dx. And I have an integral all in terms of u. Now this is inverse tangent, right? Anytime you see that, you should think of inverse tangent. So 3 times inverse tangent u plus c. Now you put your u back in. My u was x plus 1. And there's my integral. Okay. If you look, they've given you a bunch of integration formulas here and trig identities. We're not going to do this next lesson, but this page right here is so good to have. You know, you might want to hang on to this if you have to take more calculus in college, but this is really a good page to have that kind of has everything you need on it. Even a couple of things that are, you know, like these right here, the inverse trig function ones.